electrostatic constant. So I have 27 units.
Nanocoulombs? No. Coulombs? No.
Volt?
Say it again.
Volt.
Volt, yes, volt. 27 volts. If I am 2 meters away, so we tack on another meter, what is my electric potential now?
13.5? 13.5?
Volts. And we'll do one more. If I'm another meter away, what's my electric potential there?
9?
All right. So, as I get farther away from a positive charge, my electric potential gets smaller. If I put a positive charge here, I know it's going to go away from this positive charge. We got 3 other ways to explain that. But positive charges go to the lower electric potential. So, the electric potential gets smaller as we get farther from positive charging. Conversely, it gets bigger as we get farther from a negative charge. It gets bigger as R goes up from negative charge. So that's the first half of the explanation. The second half of the explanation is that positive charges move to lower electric potential. Negative charges move to higher electric potential. Because if I put a negative charge there, we know it's going to be attracted to the positive charge, or it also goes to the higher potential. And I want to emphasize again, we have not talked about voltage yet. Despite what some textbooks will say. Actually, it comes down to some textbooks are really rigid about it, and some textbooks are not. And I'll try to explain why they feel like they play fast and loose with it.
Dr. Fox?
Yes?
So, in the question, how it word like the 3 nanocoulombs is 1 meter away from.
What is the electric potential 1 meter away from a 3 nanocoulomb? That would be the word.
Yeah.
Notice that if it were a negative charge here, negative 3 nanocoulombs, that would be negative 27, negative 13.5, and negative 9. The positive charge moves to lower the electric potential, well, it lowers in that direction. Negative 9 is bigger than negative 13.5, bigger than negative 27. So the positive charge goes to the higher, goes to lower electric potential. In other words, it gets towards the negative charge. Negative charges move to higher electric potential, which means in this direction, where it's becoming less negative. Before I erase this, anybody still need this? All right, so I've got some point in space here where it is, we'll just say 100 volts, a point right here where it's 70 volts, and a point right here where it's 30 volts, and a point right here where it's 0 volts, a point right here, negative 2 volts. Assume that there's some configuration of charges that produces this. If I put a negative charge here, will it move left or right?
It's gonna left.
But, okay, it should move left, it goes to the higher potential. And if I put a positive charge, it would go,
Right.
yeah. Don't forget that the reason for part of this is Ben Franklin. He's the one who established positive and negative charges. He had no clue about the particles, so he came up with this water analogy. Things flow downhill. He pictured current as electric current as a positive charge flowing, and that would flow downhill because water flows downhill also. So electric potential, positive charges flow downhill because that's the way they were thinking. Later on, we figured out it was negative charges moving. Now, if I start here, let's get rid of those. I start here at 70 and I move to there. What is the change in my electric potential? Yeah, it's final minus initial, which is negative 40 volts. If I start from 70 and I cruise around here and I do a little loop, do some looping, and then I come back over here and loop some more, and then end up right there, what is my change in potential?
Positive 30 volts.
Say it again?
Positive 30 volts. So is it kind of like displacement no matter the path, as long as it's in that direction?
It is a lot like that, except it's not officially a vector.
Mm-hmm.
Now, in my two situations, odds are if I just put a particle there and it did this, most likely the one that went to there is positively charged and the one that went to here was negatively charged. Probably wouldn't do those loops like that. This delta V here, this is electric potential difference.
The changes?
Yes, because change is just a difference between two things. It's a subtraction. Now, electric potential difference is too much for some people to say. So they came up with a one-word equivalent. That is the same as voltage. That is voltage. So if I have a 12-volt battery, let's get that classic kind. So I got a positive side and a negative side. If this is 12 volts, all that is saying is that the potential difference between this side and this side is 12 volts. It is not telling me anything about what the potential is here, other than it's 12 volts less than that. So if this is 0 volts, that's 12 volts. If this is negative 10 volts, that's positive 2 volts. The positive side is 12 more than the bottom side. And that is because the reason why I put that up there is that, like potential energy, the actual value is not particularly important. It's the change in potential energy and change in potential which is critical here. So what drives charges to move is the voltage or the potential difference. This is what causes charges to move. I guess more likely causes charges to want to move. Whether they actually move depends on some other things. Like in a battery, I got a 12-volt difference. Yeah, those charges hopefully are not moving from the negative side to the positive side because that would neutralize the battery. And here's where some sources get lazy. This is V final minus V initial because it's change. Since I can set 0 anywhere I want it to be, why not just always set this one to 0? Let's make the initial 0. So now my change is just where whatever the potential is. And so, and since VI is 0, this we can just make that V. And so this is where they get into this, electric potential and voltage are the same thing. And they're not. But some textbooks make it look like that. Questions to here? All right, so we can now explain why charges move 4 different ways. So now we have charges moving. What do we got? Well, if I have a charge moving, this is what is known as current. And the typical symbol for current, as you would expect, is a capital I. And to answer Ellie's asked question, I don't think there's any problem where we have moment of inertia and current in the same problem.
How'd you know?
Can you see the future?
Physics.
Mathematically, it's written as the change in current over the change in time, but that's sort of misleading. This change in current, it's not like I've got 5 coulombs here, then I have 3 coulombs. It's how much charge is passing by a certain point in a certain amount of time. So if I have a wire here, my current at this point right here, I would figure out how much charge is passing by within a certain amount of time and divide.
So, you said the change in current over time, is it the change in
Change in
charge?
charge over time. I apologize if I misspoke. Apparently, I did. So if I've got a lightning strike, and it takes 2 microseconds for the lightning to hit the ground, and the charge on this is 30 coulombs, what is the current of the lightning? What's the current that's flowing through the air? Well, I have 30 coulombs over 2 times 10 to the negative 6 seconds. And I end up with 15 million coulombs per second. And of course, coulombs per second is too much for physicists. They had to come up with a one word. Coulomb per second, ampere. Named after
What does that say?
Ampere. And Marina, correct.
And the two,
That's a microsecond, that's a mu. The same symbol we use for coefficient of friction. And we will not get that far, but once you get to a certain point in electricity and magnetism, mu at that point will have represented 6 different things within the physics course. I have a video called "Do Not Confuse These Mu's." Questions to here?
it's AMPERE.
Yes. The person's name's got an accent mark over the first E. The person. Ampere. Something like that. My pronunciation is still horrible. Probably asked this before. Anyone with a decent French pronunciation? Then we are stuck with mine.
Wait, what'd you say?
Ampere. Stopped by the faculty service center this morning, and one of the things I was going to do is get an eraser for this room, and then I forgot to get the eraser. Got the other stuff that didn't do that.
You could always just use a rag and then wash it at home and it's reusable.
Yeah, the rags. Much
See,
more
we're
back to
there.
all the rag. We had some of my old diapers that were floating around.
Old
Because-
diapers.
Yeah, cloth diapers.
Wait, what?
The diapers that I had when I was a child, my mom used them as rags. And then part of my inheritance was
Like
these rags.
cloth diapers?
Yeah.
I thought you meant like regular diapers.
Those,
Like
at the time, those were the regular diapers.
I think they're like disposable diapers.
No,
I was like, why are you keeping them?
for the desiccant side.
Um,
Alright, so, all I need is a potential difference and I get charges to flow. So let's say I've got a power supply, and so the symbol for a power supply is that. Actually not circled, get that marked. This is a DC for direct current. Power supply. There are some purists out there who will say that's a power cell. You really need more than one of them. 2 power cells is what you need for a battery. Yeah, I don't play that game, but some people do. This is the symbol I'm using for a battery, for a power supply, for a power cell, whatever. I've got a voltage here. I got a 12-volt battery. Now, in a battery, there's some chemical reactions going on. I've got, well, assume it's this type. There is a barrier here. And I got negatives, a bunch of negative charges floating around here and a bunch of positive charges floating around there. And hopefully, they don't go through. If it is a rechargeable battery, then you can, by plugging it in, you can force the charges through the barrier, which will degrade the barrier, so the rechargeable batteries will lose its efficiency over time. But assuming it's a nice battery here, the barrier is still intact. These charges the negative charges want to move over to the positive charges, but again, they can't. In order to get over there, we need to somehow connect the positive and negative sides. So I can take a wire, connect it, and now these negative charges have a path to go. This is the higher potential here, higher potential, and this is the lower potential. Negative charges will travel to a higher potential, and now this is the only path they have, they will go this way. As they go, they bump into things. And you can actually, for however long the battery lasts, if you take a battery and wrap it in aluminum foil, the aluminum foil will heat up, you have a hand warmer. As the electrons go through, bump into things, and as the electron bumps into things, the atoms inside start getting a little bit more excited, and we feel that as heat being generated.
So, in like a remote control, is there like a piece of metal, like that piece of spring metal and that little blob at the end of the other side? Does it have like a little metal connected inside the remote?
Yes.
Circles around?
Yes.
And what if the negatives were to somehow cross the line and go to the positives? Would it just be a dead battery?
Yes.
Okay.
And I was driving in, we had a pickup truck at the time, and I was going around the curve, and suddenly the truck went dead completely, just stopped in the middle of the curve. Fortunately, I added some inertia there, I was able to get off to the side. What had happened is whoever changed the battery the last time didn't do it properly, and so the battery was just basically sitting there without being strapped down. It tips over, and the 2 leads touch the side of the truck. And so immediately he said, ooh, I can get over there now, not going through the barrier, but it goes as fast as the way it can. And so the battery just discharged like that.
Because the metal frame of the car was enough to ground it.
Yes.
So if you were to open a battery, what would it look like?
It depends. The batteries I've opened always has basically a battery acid inside. I guess I've basically only done it to dead batteries, but it's a gray white mess in there.
Mm-hmm.
And I've seen pictures of this, and it depends on which batteries you buy. You buy there's some big batteries about that big, about that tall. Some of those are actually just a whole bunch of little batteries, like 1.5 volt batteries. And sometimes it's cheaper to buy, if you can get the right one, buy one of those, take the top off of it, you got a whole bunch of 1.5 volt batteries.
What material do they use to conduct the positive charge and the negative charge in batteries?
To conduct it,
Yeah, but like, what do they use to represent the positive charge and then the negative charge?
what are the chemicals that are
Yeah.
used? Ooh, I forget what the positive charges are, what the material is. Not lithium, those were the, yeah, I forget. But I think Ty's about to tell us. Now, as the electrons move through, so let's go with, there's a fire in the room. And so we all try to get out of the room very quickly. What's going to keep us from getting out of the room as quickly as possible?
The size of the door.
Okay. Anything else?
There's fire in our way.
Let's assume fire's in that corner. Jennifer's the most in danger right now.
Oliver's trying to get out.
Okay.
The more faster the harder it will be to go out because we will be crowded.
Okay. So you're all focusing on that part. I was also picturing furniture to be run into. But so you picture the furniture, this is some barriers.
If we were blindfolded.
Okay, and you're blindfolded. So you're gonna run into things as you slowly work, you know that there's heat over there. You can feel the heat coming at you from over there, so you go in the opposite direction. Or there's a bunch of negative charges there, you're all electrons and you're getting repulsed by it. But as you run into things, you face resistance. Now sometimes you want resistance because if my truck had not been made of metal, if the side of the truck had not been metal, my battery would not have drained that quickly. I still probably would have gone, why is it draining? But it would not have drained quickly because that's a conductor, so you don't always want charge